In this section, we discuss the modulo multiplicative inverse. First of all, let us look at the definition. Let n be a positive natural number and a be a fixed integer. We say that an integer x is a multiplicative inverse of a modulo n if their product ax is congruent to 1 modulo n. By an abuse of notation, we often write it as x is congruent to a inverse modulo n. To understand this definition, let us first look at a couple of examples. 4 is the multiplicative inverse of 2 modulo 7, because their product is equal to 8, which is congruent to 1 modulo 7. Similarly, 2 is the multiplicative inverse of 4 modulo 7. 3 is the multiplicative inverse of itself, modulo 8. This is because, by definition, 3 times 3 is equal to 9, which is congruent to 1 modulo 8. On the other hand, 2 does not have any multiplicative inverse modulo 8. Indeed, for any integer x, it is impossible for 2x to be congruent to 1 modulo 8. Otherwise, we will have an integer that is both an even number and an odd number at the same time. This is impossible. Thus, the inverse of 2 modulo 8 does not exist. Also notice that the definition of a multiplicative inverse concerns not only a, but also n. For the same a and x, they might be multiplicative inverse of each other with respect to one n, but they might no longer be multiplicative inverse with each other with respect to another n. For instance, as we have seen in this example, when we take modulo 7, the multiplicative inverse of 2 is 4. But when we take modulo 8, the multiplicative inverse of 2 no longer exists. Now that we have seen the definition of a multiplicative inverse, the next natural question we tend to answer is clearly the existence and the uniqueness. This is actually straightforward. Actually, notice that the multiplicative inverse is defined through a linear congruence equation. Hence, the existence and uniqueness follows directly from the general theorem we have discussed regarding the existence and uniqueness or multiplicity of the linear congruence equation. For a general linear congruence equation, ax is congruent to b modulo n, we have a dichotomy. Either GCD an does not divide b. If that is the case, then we have no solution at all. Otherwise, GCD an divides b. In this case, we do have solution. Moreover, the number of distinct solutions up to congruence modulo n is precisely equal to GCD an. Now, in case of multiplicative inverse, the value of b is equal to 1. In other words, for the inverse to exist, we will have GCD a and n divides 1. But that means precisely that GCD an is equal to 1. That is, a and n should be co-prime to each other. Moreover, since GCD an is equal to 1, we obtain directly the uniqueness of solutions, that is, the uniqueness of the multiplicative inverse, up to congruence modulo n. Let us emphasize here again that if a has a multiplicative inverse modulo n, then there will be infinitely many integers, which can serve as the multiplicative inverse of a modulo n as well. However, all these integers will fall into the same equivalence class modulo n. That is the meaning of uniqueness up to congruence modulo n. With this general result about existence and uniqueness in hand, now let us turn to a special case that is really important. That is, when n is a prime number. We claim the following corollary. Let p be a prime number. Then any integer that is not divisible by p will have a multiplicative inverse modulo p. The proof is straightforward. Since p is a prime number, if p does not divide a, then p and a must be co-prime to each other. In other words, the greatest common divisor of p and a will be equal to 1. Thus, the multiplicative inverse must exist.